Okay, so we're going to talk about electrolysis, which comes from Unit 4 of the first paper. So if you're in Year 11, you should have done this by now. If you're in Year 10, there's a good chance that you've either already done it or you will be coming up to it soon. So basically what we're looking at here are keywords, and you should be thinking about keywords as the backbone of your GCSE studies. So this applies to any subject. So keywords are easy for you to learn, but then you can use them to pick up easy marks on the papers, and also you can use them to help you gain more of the more difficult marks just by applying the keywords. And I can talk more about that later on. So what you should already know, so what we're looking at is basically building on the bonding unit. We know about ions. You'd be able to spot an ion because it's got a charge, either positive or negative. You know about ionic compounds because you've done this in the bonding unit. So they conduct electricity when molten, i.e. melted, or aqueous. And ions are formed when atoms either lose, so metals will lose electrons, or non-metals will gain electrons. And again, this overriding sort of theme, opposites attract. So electrostatic forces of attraction, again from the bonding molecule. But you know about this from when you've played with magnets as a child. So what we're looking at is this definition. So this is on the first slide. So you pick up marks for this by just regurgitating it. So electrolysis, breaking down ionic compounds into their constituent elements using electricity. You'll notice that on the slide, every keyword or key phrase is highlighted sort of in yellow. And if you were going to make notes, and I don't suggest you do make notes in this presentation, you should just basically watch it. But if you were going to make notes, you focus on the keywords. Okay, so that would be a really good idea to sort of condense your notes. And what I'm saying here is that electrolysis is basically the opposite of ionization. So with ionization, you take a metal, and the metal would lose electrons or to form a positive ion, and a non-metal will gain electrons to form a negative ion. Well, electrolysis is basically the opposite. So we reverse the process. Okay. So we're going to look at a couple of different types of electrolysis. Electrolysis of molten compounds, which I think is fairly straightforward, and then electrolysis of solutions, which are a little bit more tricky and do require a little bit more thought. One thing to pick up on though is we've got this idea from physics. Physics tends to sort of get in the way of things in chemistry with this definition of current. Physics students come in and tell me that current is the flow of electrons. It's precisely the current is the flow of charge, not electrons. Electrons are charged, but you don't have to have electrons for current to be present. The flow of charge is an easier way to get your head around what's going on with electrolysis. And obviously the charged species we're talking about are ions. So again, we've got here something from the bonding unit that we look at conductivity of ionic compounds. And ionic compounds will conduct electricity only when molten or in solution. The easiest way to sort of think about this is that the ions can move. If we look at the ions in the solid, they're all in a fixed sort of position. They vibrate, but they vibrate in place and they can't move. And certainly can't migrate towards an electrode. But in a liquid, we've got that sort of random jostling movement, and in a solution, we've got the movement of ions, because when you dissolve an ion or compound, you break up the lattice, and the ions are free to move within the solution. Okay, so that's really important, but it's nothing you haven't seen before. You've seen this from the bonding unit, as I say. So what we're going to look at first is the electrolysis of molten ionic compounds. Now, molten means it's melted. So to actually cause this to happen, to cause the ionic compound to melt, you need a significant amount of energy. And you know why that is. If you think about it, you've done this before in the bonding unit. The high energy is needed because, or the high temperature, sorry, is needed because lots of energy required to overcome the many, many strong electrostatic forces of attraction in the giant ionic lattice and the forces of attraction between the positive and the negative ions. What we need to use is a DC current, so direct current. Again, physics will lend a hand here. The direct current is basically current where you've got a positive and a negative, and the current flows in one direction. It won't work with AC currents because it just keeps sort of flitting back and forth, back and forth. So DC current is what we need. And we get this idea that ions migrate to the oppositely charged electrodes. So migrate just means to move. So like birds migrate, don't they, in the seasons? So migrate. So the ions will migrate or move to the oppositely charged electrodes. So down here we see we've got the negative cathode and the positive anode. So when we switch the current on, and I've got a little power button here, when we switch the current on, we will be able to see where the ions will go. So the positive ions should move to one of the electrodes, the negative ion should move to the other. And this is all because opposites attract. So this is fairly straightforward, that if we take the negative and positive ions, they will move to the oppositely charged electrodes. So obviously this animation is just set up to make it clear that these are going to separate out and they're going to go to the oppositely charged electrode. It would obviously happen simultaneously in practice. So one of the things I guess students struggle with is this idea of reduction and oxidation. Okay, and you have to explain what happens in terms of reduction and oxidation at the electrodes. So the different electrodes, the positive anode and the negative cathode, reduction will happen at the cathode and oxidation will happen at the anode. And to help us remember this, we use a mnemonic. We'll have a look at the mnemonic in the next slide, I think. So if we use an actual example of potassium bromide, so potassium being the metal, in the ionic compound, it's obviously the positive ion, so that would have lost one electron to form the K plus ion, and the bromine would have formed the bromide ion, so gained one electron. And when we apply the current, when we switch the current on, the ions will migrate, similar to the last slide we looked at, but we get oxidation and we get reduction. So let's see what happens. On this side, at the cathode, the positive ions will go to the negative cathode because opposites attract. But to turn back, to reverse that ionization process, to turn it back into the element, we need to basically give the potassium ion, the positive ion, we need to give that an electron back. So when we have gain of electrons, this is reduction. So you can see there's a sort of equation there, K plus, and we're going to give it an electron to turn it back into the atom. So the elemental potassium, and potassium is obviously like a silvery metal. So let's see what goes on there. So all the positive ions are migrating again to the cathode, the negative cathode, and they're going to collect an electron and they will form the elemental metal. Over the other side, what we should have, well, there's a little sort of reminder there that we get reduction at the cathode. So red cat is a way to remember it, reduction at the cathode. Over the other side, what we should see is that we have the opposite. So we have the negative ions moving to the positive anode, and the negative ions will lose negative electrons, and this is oxidation. Oxidation is loss of electrons. What we're going to form here is bromine liquid. So the bromide ions will form bromine atoms, and bromine is sort of an orangey brown color. There's another equation, and we can see the ions moving across, and we can see them turn into that sort of elemental bromine, which is going to be sort of browny orange. So again, what we've got here is the idea that we're showing that the electrons are lost. So the bromine, so the bromide ion has got that negative charge because it's gained an electron to form the ion. We're reversing the process, turning it back into bromine, which is the element, and we show that by kicking out an electron. Okay, so we just sort of kick it out. We don't say Br minus an electron. We just kick it out the other side. It's easier to remember. The only other thing that we've got here is that we would have, from one bromide ion, we would only be able to form half a bromine molecule, the Br2. So half of Br2 would just be the Br atom. Okay, and we can talk about that again in a bit more detail later on. This is the mnemonic that you should use. So we've got, again, it's redox. These are redox reactions. You'll look at redox reactions in more detail if you go on to study A-level chemistry. And it's probably the more difficult part of paper one is the idea of reduction and oxidation, and what's happening in terms of electrons and what's happening in terms of these things called half equations. We're going to look at half equations right at the end. So the mnemonic is oil rig, oxidation is loss, reduction is gain. So what I'd advise you to do if you got into an exam and you were trying to remember that you got a question on electrolysis, I would just simply put that down at the side of your exam paper somewhere, and then oxidation is loss, reduction is gain, and the only things you can lose or gain really in these things are electrons. So what you would need to do is look at that and sort of, again, it's just something to help you. If you can't remember, we use this mnemonic that oxidation is loss of electrons, reduction is gain. And it's not cheating, it's just a way of you structuring your thoughts in the exam. So we're going to sort of see what's going to happen here. Reduction is gain of electrons. We're going to look again at this, this example using potassium bromide. We're going to switch the current on, and what happens is the electrons that the nonmetals lose sort of are passed through the circuit, and it's not exactly the same electrons, but you know, we've got to account for the electrons in this process. So we've got to make sure that in terms of our symbol equations and in terms of our you know, sort of half equations, that we account for all the electrons. So that demonstration really sort of tries to get the impression that the bromide ions will lose those electrons, they're pushed around the circuit, and they're actually dropped off at the potassium ions, so and they collect the electrons. So what you would form, as I said before, elemental potassium and elemental bromine. Bromine is a brown non-metal, and the potassium is a silver metal. That pretty much covers the molten ionic compounds, because the molten ionic compounds are relatively straightforward because you should only have the positive metal ions and the negative non-metal ions. One of the more sort of tricky questions that they may ask, it's not really tricky, but there's a little bit more to remember, is this idea of aqueous ions. Now, aqueous ions just means that we've dissolved them in water. So you would recognize aqueous. You see the little AQ behind the ionic compound. So it could be sodium chloride, AQ. So let's get rid of that. So what we would have is in solution, we've got the positive ions and the positive metal ions and the negative non-metal ions from the ionic compound, but we've also got H plus ions and OH minus ions from the water, and they will play a significant role in the electrolysis, because all of a sudden, instead of just considering the positive metal ions and the negative non-metal ions, we've got the water ions, so the H plus ions and the OH minus ions. There is something that we can do to sort of help us remember what's going on here. And it's basically this idea that when we're considering which ions are going to migrate to the electrodes, the more reactive ions stay in solution. Okay, so that's really important. If you want to get the top marks, if you want to get more marks than most of the students, you're going to get extra marks, almost like bonus marks, for mentioning that the more reactive ions stay in the solution. So if we were to apply the current, what we would see is that some ions move and migrate, and others will stay in solution. So eventually, when this sort of animation finishes, what we should end up with is a few ions lurking about in solution, and they would be the more reactive ions. And we'll come and have a look at that in a minute when we think about reactivity series, because it's all sort of bundled together. Okay, so we're going to look at this, the electrolysis of brine. Brine is sodium chloride solution, so saltwater solution basically. So you've probably heard of brine, sort of tuna in brine or hot dogs in brine, but it's just basically sodium chloride, which is table salt dissolved in water. So in our sort of reaction vessel here, we've got sodium ions from the sodium chloride ions from the sodium chloride, but we've also got H plus ions from the water and OH minus ions from the water. So what we've got here is a possibility of sending 2 positive ions and 2 negative ions to the electrodes, but the ions that actually move to the electrodes are the least reactive, because remember that the more reactive ions stay in solution. So what we're looking to see is that we'll deal with the hydrogen and the sodium first, the H plus and the Na plus. Sodium is more reactive than hydrogen. Okay, so you might remember that from your reactivity series. We'll look at a reactivity series later, but sodium is quite close to the top of a reactivity series, so the sodium should stay in solution. The chloride ions will move to the anode. So what we should get in theory is we should get hydrogen and chlorine produced. So let's see what happens when we switch the current on. So we're going to get hydrogen gas, so elemental hydrogen. Hydrogen is obviously H2 as a gas. And then over the other side, we've got chlorine gas, so the elemental chlorine. Now we know we've got gas on either side because we've got these bubbles or effervescence. Now effervescence is just basically when you've got a gas produced in a liquid, so you get bubbles produced, so you can see the bubbles and you can hear fizzing. So that's what happens at the electrodes. So what we're left with in solution is sodium hydroxide. And sodium hydroxide is our third sort of product, because we have already the hydrogen gas, the chloride gas, and now we've got our sodium hydroxide in solution. So I'm going to get rid of these annotations and we'll have a quick look and see what happens. So let's see. So when the hydrogen moves to or migrates to the cathode, the H plus will collect an electron and form hydrogen atoms. So that is obviously reduction. Over the other side, we've got a chloride ion migrating to the anode and sort of depositing an electron, kicking an electron out. It kicks the electron out, and that is obviously oxidation, because you can't have one without the other. And then what we're left with is the sodium. So one of the things you're asked to do in exams is you're quite often asked to provide a series of tests for certain things. So test for chlorine gas, test for oxygen gas, test for carbon dioxide and all that. So this electrolysis of brine, because we produce 3 significant products, we can test for these 3 significant products. So this unit actually covers quite a lot of easy marks that you can mop up and really feel confident going into the second part of the GCSE course into paper 2. So what we have, if we switch the current on, the sodium chloride solution, or the brine, will yield hydrogen gas, chlorine gas, and sodium hydroxide. So you get marks for being able to tell me, or tell the examiner, sorry, that you know the test for chlorine gas. Now chlorine gas will obviously bleach litmus paper, so it strips the colour out of anything with a dye in it. So litmus paper or universal indicator has a dye in it, so chlorine gas would bleach that, so basically strip out the colour. So you can just use the word bleach. So hydrogen gas, test for hydrogen gas, we know hydrogen explodes with a squeaky pop. There it goes. So only hydrogen gas will explode with that squeaky pop, and you've got to mention squeaky pop. I know it sounds daft, but there you go. And then sodium hydroxide will turn universal indicator blue or purple. So I've got a little pipette of universal indicator. We know we've got sodium hydroxide in the solution, so if we add a couple of drops of sodium of universal indicator to the sodium hydroxide, it should turn that purpley lilac blue colour. So this is something I referred to before as a sort of like a reactivity series. And you look at this very early on in the GCSE chemistry, and it's the idea of sort of a displacement reaction. So if we pick on carbon, carbon will only be able to displace elements below it in the reactivity series, so less reactive elements. So your definition for displacement was a more reactive element takes the place or displaces a less reactive element in a compound. So all of these elements can be extracted by smelting. Now, smelting is just basically heating it up in a furnace with carbon. So you heat the ore up with carbon, and the carbon is able to displace the metal from the ore. So ores are usually oxides. So we could think of, I don't know, a classic example is iron oxide plus carbon. This isn't, we usually use carbon monoxide, but it's the same thing. So let's see, carbon monoxide. So we're going to need 3 of them, and that will displace. So the carbon will take the place of the iron in the compound. So the iron is kicked out. So a displacement reaction, and then the carbon just teams up with those 3. So we end up with 3 CO2. So that works because the iron is less reactive than the carbon. On the other side, though, or sorry, above it, the carbon won't be able to displace these more reactive metals from ores. So usually when we've got a situation where we can't use carbon, and we use carbon because it's cheap and readily available, where we can't use carbon, we use electrolysis. So one of the things that we need to look at as part of your course is the electrolysis of aluminium oxide. Okay, so we're going to look at extracting aluminium from aluminium oxide. So we know we can't use carbon, so we can't sort of go through that smelting process. So we have to use electrolysis. Now, aluminium is expensive, and it's expensive for a couple of reasons. And it's not because aluminium is rare. Aluminium is the most abundant metal in the Earth's crust. It's expensive because of what we have to do to extract the aluminium. The first thing, the first sort of wave of expense is we have to have molten aluminium oxide, because we can't really dissolve this in solution because that wouldn't give us the aluminium. The aluminium would stay in solution. So what we need to do is get the aluminium oxide to melt. Now this is difficult, or not difficult, it requires a high heat, so a high temperature. Because it's an ionic compound, and we know that ionic compounds are difficult to melt because they've got that very high melting point, because lots of energy needed to overcome the many, many strong electrostatic forces of attraction between the negative ions and the positive ions in the giant ionic lattice. So to cause it to melt, we have to use tons and tons of heat, and if you're doing this industrially, so you're doing this on a large scale, it means that the fuel bills are going to be really, really high. The other reason why it's expensive is there's another fuel bill. It's the fuel bill in terms of the electrolysis. We have to provide an electric current for this to work. So it's sort of, there's 2 huge energy bills, one to melt it and then one to electrolyze it, one to sort of generate that current and apply the current to the molten solution, the molten mixture, sorry. So what we do is we use cryolite. Now cryolite's a key word, and there's marks up for grabs here. Cryolite is added because it lowers the melting point of the aluminium oxide. one thing I will say, just understand it's not a catalyst. So cryolite is not a catalyst. It just lowers the melting point of the aluminium oxide. So the mixture has got a lower melting point than just using aluminium oxide alone. Now, you don't have to explain it, but you just have to make reference to the fact that they use cryolite to lower the melting point of the aluminium oxide. Now, in industry, this has obviously got significant benefits in terms of cost. So if it's got a lower melting point, there's less energy needed. So the outlay, the fuel bills are lower. You can do it quicker, a little quicker, but more significantly in terms of the environmental impact, anytime you're sort of trying to get these huge temperatures or high temperatures in industry, you're basically relying on fossil fuels. So if we're burning fossil fuels to melt the ionic compound, it's going to be generating CO2 gas. Okay, so there's that sort of carbon dioxide, which is a greenhouse gas, which is causing global heating or climate change or whatever. Okay, so it's significant. Any opportunity to reduce a melting point or reduce the temperature, the activation energy or whatever, you take it in industry because it will end up being a cheaper process. So here, what we've got is that the whole sort of wall of the vessel there, the outer case of the vessel is the negative cathode. Okay, so the cathode is the wall of the vessel. So the positive ions will migrate to the wall of the vessel. Up top, we've got this thing. It's a graphite anode. So the positive anode is made of graphite. And if you remember, graphite is just a very pure form of carbon. Okay, so let's see what happens. The cryolite doesn't get involved. The cryolite just helps us have that low melting point. So I'm going to apply the current and let's see. So the positive ions again to the negative cathode and the negative ions to the positive anode. So what we will see is that we get sort of two products. We get the aluminium that we're looking for as a liquid, and basically the reaction vessel will fill up with aluminium as the positive ions hit the side of the vessel, i.e. hit the cathode. They will collect electrons and form elemental aluminium. As the negative ions hit the cathode, hit the anode, they will lose their electrons and form oxygen. But significantly, if we look at our anode here, we've got carbon dioxide being produced. Now there's no carbon in the mixture, in the aluminium oxide and cryolite mixture. So the carbon dioxide is produced when the reactive oxygen is produced at the anode, because we've got O2 minus going there and producing oxygen, and we're going to kick out, in this case, 4 electrons. But because we've got really sort of high temperature, a really high temperature, and the reactive oxygen and the carbon, basically the carbon and the oxygen react together and produce carbon dioxide. So over time, what will happen is that the anode will sort of shrink. It will be reduced in size, because when the oxygen reacts with the graphite, you can see it shrinking there. When the oxygen reacts with the graphite, the carbon dioxide gas escapes, so it's taking that mass of carbon within the anode, and it's causing it to shrink, and eventually they shrink that much that they need to be replaced. So that could be maybe every 4 weeks or whatever, it might need to be replaced. The reason why we're looking at that is because it's another chemical reaction, but it's another question that they could ask you where you could pick up marks. So the final thing we're going to look at now is these half equations. Now, half equations, as I've mentioned before, it's possibly an area where students struggle and they get sort of quite anxious about it. You shouldn't be. Half equations are just basically what we're looking at in terms of reduction and oxidation. Now, we've looked at several half equations in this presentation already, and I haven't made direct reference to them because I didn't want to make a big deal, because there's no need to get a big deal and make a big deal, because they're actually relatively easy once we understand what's going on. And it goes back to this idea of reduction and oxidation. And if you remember your keywords and the definitions and the mnemonic, we remember reduction is gain of electrons and oxidation is loss of electrons. So here I'm going to use an example that we looked at first with the molten potassium bromide. So we've got the reduction, the potassium ions gaining electrons. We've got oxidation as the bromine or the bromide ions, losing electrons. So these are two half equations, and basically they're just two halves of an overall equation, and one deals with reduction and one deals with oxidation. And if you're unsure what you're looking at, just go back to your definitions. Reduction is gain of electrons. So here we can see the potassium ion gain an electron, so that's reduction. The bromide ion losing an electron but kicking one out, so that's why that is oxidation. Oxidation is loss. Okay. So when you're given half equations, sometimes they might ask, and it's always good to know what to do here, sometimes they might ask to complete an overall equation. Now the overall equation here, we just put the two things together. So what we would be looking to do is construct the full equation from the two half equations. Now again, it looks complicated, but it's not. Don't worry, because if you know how to read an equation properly, you'll know that you have reactants before the arrow. So if we've got two half equations, we've got two lots of reactants. Okay, so anything before the arrow are the reactants, and that's what you put down in the overall reaction. Over the other side of the arrow, we've got our products. And here, because we've got two half equations, we've got two lots of products. So we put them down. And just like any sort of equation, whether it's in maths or in chemistry or whatever it is, if you've got things either side of the arrow, we can cancel out. So this would be like either side of the, equation in maths. So we can see that we've got here one electron and one electron there. So we've got an opportunity to basically cancel those out. So we're going to get rid of that, and we're going to get rid of that, and then we're just going to bring everything down to get the overall equation. And all we've done is used our sort of year 7 knowledge of chemical reactions, where we've got reactants before the arrow, products after the arrow. We sort of combine the two sets of reactants and the two sets of products, and see what we can cancel out to make the actual reaction simpler. One final thing we'll look at in terms of half equations, and this is the last slide in the presentation. One final thing that you need to look at, sometimes they give you ions with multiple charges. So we're going to go straight for our aluminium oxide, so the electrolysis of aluminium oxide. So here we've got reduction and oxidation. So again, if we just apply the definitions, reduction is gain of electrons. So the aluminium 3+ is gaining 3 electrons to negate that 3+ charge. The oxidation is the O2- losing those 2 negative electrons, or the 2 negative charges, 2 electrons, kicking them out to form the oxygen. But the process is essentially the same. However, when you've got multiple ions, if we've got, say, in this instance, we've got a 3+ and a 2-, it might be difficult to think of how to balance them. So what I've suggested is that you look at this and look for the lowest common multiple. And it's the lowest common multiple of the electrons. So we're going to balance the electrons. So we've got 2 electrons there and 3 electrons there. And if your maths and my maths is any good, the lowest common multiple of 3 and 2 is 6. So how many of these, 3 lots of electrons do we need to make 6? And how many of these 2 lots of electrons do we need to make 6? So I'll go through this quite slowly. We need 2 lots of the 3 electrons to make 6. And what that does is it means that we multiply everything in this half equation by 2. So we end up with 2 aluminium 3 plus, 6 electrons, because the 6 electrons are basically, what are we looking at? Those 6 electrons are 2 lots of 3 electrons. The 2 Al is 2 lots of the aluminium. And then the Al there, well, with 2 lots of the Al, because we've doubled everything, because we're trying to get these electrons to make up to 6, because it's the lowest common multiple. Over the other side, or with the other half equation, sorry, we need to make this these 2 electrons up to 6. So we multiply that by 3. So everything is multiplied by 3. Okay, so let's see what we end up with. We end up with 3 lots of O2, 1.5 lots of O2, because it's 3 times a half is 1.5, and then 3 times 2 is 6. And once we've done that, it's just a case then of doing what we did before. We combine the 2 equations, but when we're combining the 2 equations, the 2 half equations, we'll focus on the ones that we've actually sort of adjusted to balance everything out. So we've balanced it before we actually bring it down. So again, same process. We've got 2 lots of reactants. That will give us the reactants in the overall equation. We've got 2 lots of products, so we bring those down and make the overall equation. We look to see what we can cancel out. So obviously we've got 6 electrons on that side and 6 electrons on that side, because that's the whole point of trying to balance the electrons on each side, so looking for the lowest common multiple. And then we just drag down everything that's left, and that gives us our overall equation. Okay.